Okay.
So, hello everyone and welcome. It is a pleasure to introduce Professor Taeko Wydell, who is from Brunel University. She completed her PhD, which was funded by the ESRC at Birkbeck with Max Coulthart and Caroline Patterson, and then also worked as an MRC research fellow at UCL until 1994. And then at 1994, she was the first psychologist to be awarded a 4-year Wellcome Trust postdoctoral research career development fellowship at UCL. After that, she moved to Brunel, where she is currently, and I was very lucky to be able to join Taeko when I started my PhD. So I'm very, very, very happy that she agreed to come and give a talk for us today, which is on developmental dyslexia in different languages, looking at behavioral dissociation and biological unity. Taeko, whenever you're ready.
Yeah, okay, thank you very much, everybody. It's going to be I have a lot of slides to show you, so it might be a bit fast. So here's my title, as really kindly described. So this is my framework of my talk. I'm going to talk about what is developmental dyslexia, behavior dissociations in reading processes across different orthographies, then cultural diversity in the neuroscience of reading across different orthographies, and then biological unity in dyslexia across different orthographies, and then cultural diversity and no biological unity, an anomaly, and then I'm going to give you a summary. So what is developmental dyslexia? So dyslexia is a specific learning disability that is neurobiological in origin, and dyslexia is highly heritable, with an estimated 30 to 50% chance of being passed from parent to child. This is the study from behavioral genetic research, and genetic linkage analysis has identified regions of the genome that might have an inherited variant that cause reading disability. And this is research from molecular genetic research. And behavioral manifestations of dyslexia result largely from a deficit in phonological component of language, and this led to a phonological deficit hypothesis. So this is the definition, current working definition from Rose Review. Dyslexia is a learning difficulty, as I've said before, that primarily affects the skills involved in accurate and fluent word reading and spelling across the range of intellectual abilities. So it doesn't really matter whether you have high IQ or low IQ, it happens to all the intellectual abilities. Characteristic features of dyslexia are difficulties in phonological awareness, verbal memory, verbal processing speed, and often you see dyslexic children with other developmental disorders like SLI, specific language impairment, poor comprehender, dyspraxia, dyscalculia, ADD, ADHD. However, these are not by themselves markers of dyslexia. And phonological awareness and phoneme awareness, and this is the kind of phonological awareness, the umbrella term, and a sentence can be broken down into words, into syllables, and syllables into onset and rhyme, cat as cat, and rhyme and alternation, do the TED rhyme with head, and into phonemes. Phoneme is the smallest speech sound unit. And so for phoneme awareness skills, you have to be able to phoneme isolation, phoneme blending, phoneme segmentation, phoneme addition, deletion, and substitution. And often dyslexics are typically poor at performing phoneme awareness skills tasks. Phonological deficit hypothesis. This actually hypothesis seems to be the major hypothesis which can describe or account for developmental dyslexia, and particularly very prominent for the last 30 years or so. And researchers like Wagner, Zerps, and Wood would say that phonological processing is a signature cognitive linguistic skill that is essential for the development of reading regardless of the script. And this deficit in phonological processing is regarded as contributor to most of cases of dyslexia. And then, of course, other visual deficit hypotheses like magnocellular abnormality hypothesis and VAS visual attention span deficit hypothesis are around, but I'm going to concentrate on phonological deficit hypothesis for today's talk. So Ramiu conducted experiment with 16 dyslexic and 16 control university students in order to test the following theories of developmental dyslexia: phonological theory, rapid auditory processing theory, and cerebellar theory, and magnocellular theory. And results show that all 16 dyslexic students showed a phonological deficit. This is 100%. And 10 showed an additional auditory deficit. Another 4 showed an additional motor deficit, part of cerebellar theory, and only one showed additional magnocellular deficit. So the results strongly support the phonological deficit theory of developmental dyslexia. And Ramiu also conducted a review and looked into following hypotheses of 1, 2, 3, 4, 5 hypotheses. Auditory deficit, for example, Talara's work, dyslexic auditory processing is impaired specifically on the short sounds and the faster transition. So when you say short sound, usually consonants are very short, transient, and vowels are steady state. So these dyslexic individuals find it very difficult to identify consonant rather than vowels. So this actually can account for 45%. Sorry about this. And visual stress, this is Wilken et al. Study. And sometimes colored overlays or glasses can help read, but the actual data are not quite available. So Ramiu cannot give us any percentage. Magnocellular dysfunction can account for 29%, and motor deficit, cerebellar dysfunction, can account for from 30 to 50%, depending on the empirical studies that Ramiu reviewed. And phonological processing deficit, according to Ramiu, can account for 100% of developmental dyslexia. So these are the 10 commonly used tests of phonological awareness, and particularly phoneme segmentation, phoneme blending, phoneme deletion. Those seems to be quite effective tests, particularly when you want to test children. So phonological awareness is the awareness of the sound of words, one aspect of metacognitive knowledge. Phonological awareness is explicit knowledge about our language processes, which we can make deliberate use. And even with adults with child diagnosis of developmental dyslexia have shown persistent phonological deficit. And adults with developmental dyslexia were impaired compared to controls on RAM, rapid automatized naming, phonological awareness skills test, and non-word reading. And even the well-compensated dyslexic adults who do not show any impairment everyday lives, showed, particularly those university students, showed residual phonological deficit on the phoneme deletion and spoonerizing. And spoonerizing is a test where you are given a pair of words like car, park. You have to swap the initial phonemes. So car, park becomes par, cark. Okay. So now I'm moving on to behavioral dissociations across different orthographies. So English, this is the prevalence of dyslexia. In the English-speaking world, the prevalence of dyslexia is around 10 to 12%, forming a large minority group. The prevalence of dyslexia in consistent or transparent orthography is lower. For example, in Italian, it is around 3 to 4%. In Japanese, prevalence of reading difficulties differs across different scripts. So I say we, because I'm Japanese, we use 3 different scripts. One is syllabic hiragana, the other is syllabic katakana, and the final one is opaque logographic kanji, which is similar to Chinese characters. So it's only 0.2% in transparent syllabic hiragana, 1.4% in transparent syllabic katakana, 6.9% in opaque logographic kanji, even 6.9% of prevalence in logographic kanji is less than 10 to 12% of English. So now we are going to uncover why dyslexic form a large minority group in English-speaking world. So this is the type of written languages available worldwide. Alphabetic script, the basic unit represented by grapheme is essentially a phoneme. So these are used by English and other European languages. So the word cat has 3 phonemes, cat. And consonantal script, those are used by Hebrew and Arabic. Not all sounds are represented as vowels are not written down. However, when children start to learn Hebrew or Arabic, vowels are written in. So these children start with a very transparent writing system, and then suddenly is not quite the right word probably. Around 12 years of age, the vowels will be removed from their writing. So this is now an adult writing system akin to, for book, bike, bake will be all written like sort of BK. So it's very much sort of contextual. You have to know contextually whether you are talking about book, reading about book or bike or bake and so forth. Hence, quite opaque. And then written syllabic script, written unit represent syllables. These are used by Cherokee and Japanese Kana. So Japanese Kana, or Japanese word cat, is neko. And in Japanese kanji, it's written in 2 characters, neko. So 2 syllable, 2 character word in Kana. Now, logographic, ideographic script, each symbol represents whole character word in Chinese, and their language is, well, I try best. Mao, meaning cat, 1 syllable, 1 character word. Japanese kanji, we have similar characters here, but as we say in Japanese, cat is neko. So 2 syllable, 1 character word. So that's the kind of difference between Chinese and Japanese kanji. Now looking into English orthography is a little bit more, and on your right-hand side, you can see voice onset time for ba and pa. So ba and pa, the difference between the voice onset time is only 40 to 60 milliseconds. And as you can see, the a sort of in the vowels, as I said, steady state. So it's something very similar. So difference between ba and pa is only 40 to 60 milliseconds, and yet we understand whether we had bat or pat. And English has 44 phonemes, and 44 English phonemes can be divided into 2 major categories, 24 consonants, 20 vowels. 44 English phonemes are represented by the 26 letters of alphabet individually and in combination. And in English, there are 1,120 ways of representing 44 phonemes by different letters or letter combinations, which are called graphemes. So the another characteristic of English writing system is English has letter names and the letter sound. Letter A has the letter sound A. Some languages like Italian, there's no difference between letter names and letter sound. So how inconsistent phoneme to grapheme correspondence in English? I'll give you some example. Take an example of sound, the phoneme of f. As you can see, 1 F in fun, 2 Fs in cliff, PH in phone, GH in laugh, LF in calf, and FT in often. And then long vowel E is the same. So there are so many ways of transcribing this sounds E, B, C. Okay. So English has one of the most complicated grapheme to phoneme correspondences. For example, Glasgow would say that we can categorize monosyllabic English words into 4 consistent regular words, ink, link, pink, or mink. So these words, the word body ink is always invariably pronounced as ink. And then consistent irregular words, normally hint, tint, lint, word body int is pronounced as int, but there's one enemy, pint. So you have to know how to pronounce this kind. And cave, pave versus have is the same. And then in consistent words, the vowel, two vowels together, EA, is pronounced in 4 different ways. Beak, peak, leak versus red, head, spread versus stake, this is only one, and then learn and earn. And exception words, for example, OUGH word body, whenever it appears, pronunciation changes. Okay, and then there's another type of exception word like yacht and kernel. If you follow the rules of grapheme phoneme translations in English, some may read it as yacht or kernel. So for reading English, phonological awareness skills, phoneme awareness skills are absolutely essential. Now we are looking into orthography, English orthography versus Italian orthography. Sorry about this. So English, as I said, 1020 graphemes are represented by 44 English phonemes. The mappings from grapheme to phonemes one-to-many. The English language has letter names and letter sound, while Italian, which has much simpler GPC, grapheme to phoneme conversion, in Italian, 33 graphemes are sufficient to represent the Italian 25 phonemes. Mapping from grapheme to phonemes is always unequivocal one-to-one. So interestingly, the young Italian children can achieve 92% accuracy on word reading test after only 6 months of schooling. So Italian children acquire reading and writing skills more easily and faster than English children. So Marinelli et al. Show that Italian children were very accurate in spelling in Italian after only 2 years of schooling, while English children were still not accurate at spelling in English after 5 years of schooling. So if you take the dual root cascade model reading to interpret all these data, you can actually identify which is the most optimal reading routes and so forth. So according to dual root perspectives, there are 2 routes are necessary for reading. One is sublexical grapheme phoneme conversion rules, and the other one is lexical access, orthographic input lexicon, phonological output lexicon, as well as via semantic route as well. So in fact, 2 routes are available for lexical reading. So for Italian, optimal reading route is GPC route because grapheme to phoneme conversion is so always consistent and one-to-one. However, this does not preclude access to lexical route, especially familiar or high-frequency word. And we will see the evidence for that in a minute. For English, the optimal reading routes are the lexical routes, a dialect lexical route bypassing the semantic system, and lexical route via semantic system. Now, Forrest et al. Conducted the behavioral neuroimaging studies back in 2000, and behavior task. Participants are 36 English students and 36 Italian students. And stimuli are, apart from the high-frequency word from their own languages, both English and Italian students get 2 types of words and 2 types of non-words. And I think their stimuli are so well controlled, and I'm so impressed with their work. International words from Italian, villa pasta, international word from English, boiler basket, non-word from Italian, ponde from ponte, moco from moto, and non-words from English, cabin from cabin, marnet from market. So what sort of result have they got? As you can see from this graph, regardless of words, whether it's derived from Italian or words or non-words, with non-words derived from Italian or English, always Italian participants are much faster, significantly faster to pronounce these words than English participants. And English participants, there's no difference between non-words derived from Italian or derived from English, while Italian show non-words derived from English took longer to name than the other stimuli. Now, international words, international words conforming to Italian much faster than English. Italian much faster than English, but Italian words conforming to English, more or less the same between English and Italian. So how do Prof interpret the data? I'm going to show you later on, okay? The inconsistent orthographies, errors in reading are relatively rare, and most apparent symptom of dyslexia is reading slowness, lack of fluency. Inconsistent orthographies, length effect has been used as a benchmark for reading strategies in children, and length effect refers to the phenomenon that longer letter strings, word or non-words, are read more slowly than and less accurately than shorter letter strings. So length effect a sequential operation of a sublexical reading mechanisms, and that's why it's used as a benchmark. So this is a result from Zoccolotti et al.'s children with grade 1 and 2, neurotypical children from grade 1 and 2, with grade 3 dyslexic children. So RTs of control, reaction times of control participants become shorter and less sensitive to word length effect. And RTs of dyslexic participants were significantly longer than those of the same age group. So this is dyslexic group, and this is second and third, and particularly third grade neurotypical children. And RTs of dyslexic participants were similar to those of the first graders, both showing clear length effects. So Zoccolotti et al. Said that reading improvement can be due to either to improvement in the efficiency of the sublexical procedure, so they can so much faster to translate from grapheme to phoneme, but they might have acquired the lexical procedure. So the abrupt transition observed from first to second grade suggests that in normal neurotypical development, the lexical procedure is already predominant in second grade. So it's somehow they acquire this lexical strategy much earlier. So, already second grade and third grade. So English and versus Italian, it's not a football, it's English word. And okay, English speaking word, prevalence of dyslexia is around 10 to 12%. I've said that before. And dyslexia affects skills involved in accurate and fluent word reading. Both accuracy and fluency matters. And the Italian, prevalence was much lower, 3 to 4%. And the dyslexia primarily affects skills involved in fluent word reading. Remember, Italian children can get 92% of accuracy even after 6 months of education or primary school education. So accuracy, you don't actually see any impairment, but fluency, the latency. So from dual root perspectives, 2 routes are available, I said sublexical, lexical route, and Italian, we've seen the optimal reading route is GPC, but this does not preclude access to lexical route, and indeed young children even establish lexical route fairly early on. And for English, optimal reading route is very much lexical route, because grapheme phoneme conversion route doesn't always give you the correct pronunciation of a word or non-word. So now moving on to case of Japanese orthography. So as I said before, we have 2 corrective different scripts, syllabic kana, 1 character per 1 mora. Mora is something similar to syllable. Hiragana, grammatical morphemes and function words. And katakana is used for foreign non-words, camera, computer, and so forth. And the logographic or morphographic kanji, and 1 character with multiple pronunciations. So nouns like gakusei, have a look at the root morphemes of inflected verbs, now becomes manaru. And bijin, beautiful lady, in nouns, but look at the adjectives, utsukushi, now bi becomes utsuku. And then bosatsu, very busy, in noun, it becomes isogashiku. So you can see, depending on how these combination of these characters appear in nouns or adjectives or adverbs, pronunciation changes. So learning to read kana, as you can imagine, very easy and effortless. And all the Japanese speech sound can be transcribed in hiragana or katakana. On the other hand, learning to read logographic or morphographic kanji is rote learning and effortful. And this is the same for learning to read in Chinese. Often the motor sequence of these characters will help you retrieve the correct characters. And I tell you how. Okay, so this is the page from primary school child notebook. He's trying to learn new kanji characters. So we write from top to left. We write from top to down, from top to down, and then from right to left. And then you can actually repeat when you have to learn new kanji characters 10, meaning heaven or sky. They have to write down 12 times. And each time you have to say 10, 10, 10, 10, 10, 10. So by the time you practice this 12 times, sometimes 20 times, your motor sequence, motor kind of in the sequence can be remembered by your hands and arm. So one of the peculiar sort of things that we Chinese character users or Japanese kanji character users would do is writing in the air. If you don't know, if you're not too sure about kanji characters or Chinese characters, they write in the air or write it in your palm. And you never see anything like that in any other writing system users. Okay, so we tested individually 500 grade 2 and grade 6 Japanese primary school children, and 16 tests, including reading, writing, phonological awareness skills, vocabulary size, IQ, and other cognitive tests. And this was published in 2009 in Reading and Writing. So some of these are sample tests. So non-word backward repetition. You give a non-word like kalome. You have to say meloka. You have to reverse order. So it can be quite difficult. And standardized word picture matching test. This is to test the children's vocabulary. And this one is which one is collaboration out of 6 pictures. The correct answer is this boy and girl carrying a pail of water, because if they don't cooperate with each other, water will spill. And then we use the rapid automatized naming test. We use the mixture of numbers and pictures. And then we also used Ray-Ostrich complex figure test, copying, immediate recall, and delayed recall to test children's visuo-spatial processing skills. So results showing that vocabulary size, ST-tau best predicted kanji reading performance of grade 2 to grade 5 children. And vocabulary size, ST-tau, and phonological awareness skills, non-word reading and repetition were the important variables for predicting kanji reading performance of grade 6 children. So only older children show the phonological awareness exert its influence on their kanji word reading. So based on this paper, we actually developed for the first time the 2 standardized tests assessing literacy development attainment of Japanese children aged 8 to 18, as well as screening tests for dyslexia, straw R and straw R. So now we can actually test children aged from 8 to aged 18. So this is the very first standardized tests available in Japan, and we're very proud of that. Okay, so length effect and lexicality. So we, in this paper, just like length effect, lexicality effect in Italian, Zuccolotti et al.'s experiment, we tested 59 typically developing children from preschool to primary school, grade 5 and 6, and 6 developmental dyslexic children from grade 5 and 6. So task for reading aloud 2 character and 5 character string letter hiragana, katakana was unknown words. So these are the results actually seen here. So reading latencies in hiragana, So this is 2 and 5 dyslexic 5-6 children, and this is two character and 5 character words non-word. This is the same age group neurotypical children result. And as you can see, the hiragana was oldest children in this group don't show significant length effects at all. You start to see some length effect in non-words. And while here, the same age group, but dyslexic individuals show much greater length effect here. And less so, somewhat less for non-words. We don't know why, although latency is much longer. And then this is katakana. You started to see very clear length effect with dyslexic children, 5 and 6 grade, and the same age children, 2 and 5. You started to see again similar effect. You see tiny bit more of length effects in katakana, and we believe this is because katakana is less frequent than hiragana. And then compared with lexicality by length interaction in Italian children, something very similar. Okay. So now moving on to the case of Chinese orthography and phonological awareness. So Huan and Hanley tested 8-year-old primary school children from Britain, Hong Kong, Taiwan on phonological awareness skills and visual skills in relation to reading skills. And phonological awareness skills were significantly related to the reading ability of British children only, but not Chinese children in Hong Kong or Taiwan. Visual skills, on the other hand, were significantly related to the reading ability of the Chinese children in Hong Kong and Taiwan, but not British children. So Huan and Hanley suggest that phonological awareness skills are not as important and crucial when Chinese children learn to read as British children. So that's already a difference here. So we ask the same question, are phonological awareness skills important when learning to read in Chinese? We conducted 2 different studies. One published in this is PROS 1, and the other published in Reading and Writing. Okay, so with various colleagues of mine. So first one is Wei et al. 2014. We tested 400 Chinese children, preschool and year 1 to year 3 primary school children on phonological awareness skills, morphological awareness skills, and orthographic awareness skills. Now, phonological awareness tests is something similar to phoneme deletion. And morphological awareness task is given the prime sentence. Early in the morning, we can see the sun rising. This is called the sunrise. And test sentence is we made up. At night, we might also see the moon rising. What could we call this? The correct answer is moonrise. And orthographic awareness tasks, we are given 2 characters, which are non-word characters. And one needs non-character, which violate orthographic regularities, and the pseudo characters, which was made up based on the rules of Chinese orthography, but you cannot pronounce them because they are non-words. And then results show that orthographic awareness skills best predicted younger children's reading performance around sort of grade preschool and grade 1. And morphological awareness skills better predicted older children's reading performance than younger children's, so grade 2 and grade 3. And phonological awareness skills become an important variable for predicting reading performance only when children were older, grade 3. So this is despite the fact that these children are from mainland China and they do learn Chinese kind of alphabet, pinyin, and yet they don't show phonological awareness skills effect until older children. So results are similar to those of Japanese children when learning to read, but different from the English-speaking children when they are learning to read in English. So this is Wydell and Weiss study. We tested 19 children, neurotypical children, and 19 18 typical development, 19 dyslexic children aged 9 and 18 typical developing children aged 9, plus 24 typical developing but younger and reading age matched children. So age matched control and leading age control participants. So we did all the essential typical tests that we tested children. The only difference is we included visuo-motor integration test. This is what we wanted to test. So this is visual integration test. 6 geometric figures were printed on a sheet of paper, and the participant children were asked to copy the figures without the time limit. The geometric figure stimulus becomes increasingly more complex. So this is the kind of new test. We have some hypothesis, so included this, and then result, and we also included run numbers, and we actually came up with some interesting. Okay, so from this experiment, I didn't show the result. The orthographic test processing skills and visuo-motor processing skills and also morphological awareness tests all came up significant. But most important variable was visual-motor integration test. And the dyslexic children show a very impaired performance on this visual-motor integration test. So that's what happened. Sorry about that, I didn't. So putting all the experiment together, those cognitive skills important for learning to read in Chinese and Japanese are vocabulary size for Japanese, visuo-spatial processing skills, Chinese and Japanese, orthographic awareness skills, Chinese, morphological awareness skills, Chinese, visuo-spatial, visual-motor integration skills. This is both Chinese and Japanese. So the story thus far, different cognitive processes are involved in reading in different orthographies, which are primarily due to the different characteristics inherent within a given orthography. These differences give rise to different prevalence rates for developmental dyslexia. So, is it just a theoretical possibility then to suggest that we should be able to find an English-Japanese bilingual with monolingual dyslexia in English? Now, I'm going to show you behavioral dissociation within the bilingual individuals. The first cognition paper came out in 1999 with Professor Brian Butterworth from UCL, and then second one came out in 203 with my colleague, Professor Tadashisa Kondo, and the third one, the behavioral neuroimaging research came with Professor Tadashisa Kondo in 2015. And the last one with Professor Mutsuo Ijuin is the actual computer simulation model. Mutsuo actually simulated this hypothesis of granularity and transparency. So something rather different, but interesting. Now, orthographic. So in order to account for the differences in the prevalence of developmental phonological dyslexia across languages, Wydell and Butterworth postulated the hypothesis of granularity and transparency. So okay. So we have two axes. So one x-axis is granular size, whether it's phoneme, syllable, word, whether it's fine or coarse, and transparency on the y-axis is transparent or opaque. So we can actually plot all the non-writing systems in this plot. And we hypothesize that phonological dyslexia would be rare in two conditions. Orthographies where print-to-sound translation is transparent, one-to-one, regardless of the level of translation, albeit phoneme, syllable, or character. And even in opaque orthographies, the smallest orthographic unit representing sound is coarse, larger grain size, such as whole character or word. They won't produce many phonological dyslexic individuals. So these, all the writing systems under this gray area, they don't produce many phonological dyslexic individuals. So that's our prediction. And now let's just look at the AS's performance on phonological awareness reading, and as well as other cognitive tests in both English and Japanese. And we included Japanese and English control participants. So this is the result of phoneme categorization test. One end is sound of P, the other end sound of key, and these are digitized and gradually closer to P start with gradually closer to key. Okay, and then all you need to do is, did I hear P? Yes, right hand key. Did I hear key? Then you press left hand side key. And this result is actually typical of English native speakers' perception of P key or suzu. And in fact, I also did the same experiment, because in Japanese we have P and key sound. Mine came very zigzagged. So I wasn't kind of hearing English phonemes. I was hearing Japanese syllables. So that's already kind of different here. But AS is typically, in that sense, native English speakers. Okay, so this is AS's test in English, and Brian and I worked so hard to collect first data. This is this one. We compared English controls on phonological awareness test in English. AS's performance is significantly impaired on every test we conducted. Significantly was, as you can see. And then we compared with my colleague, Professor Kondo. We compared, by then AS was university student. We compared again, this time, both English and Japanese controls, rhyme judgment, phonological lexical decision task. You have to say yes to BRANE, and orthographic lexical decision task. This is a spelling test, and then also reading. Every test we conducted, it was significantly impaired, not only the performance of English controls, but also Japanese controls. So he is typically phonological dyslexic in English. Now let's just look at the Japanese data. These control data are Japanese university students. And as you can see, in Kanji word, latencies, not significant result at all, and accuracies, hardly any significant. Actually, AS is doing extremely well, except exception word. Those are the ones that, unless you know this word, you cannot pronounce. And AS was only 16. By the time, if he stayed on in Japan and went into Japanese university, he'd have been reading these exception words quite easily. So I'm not really worried about that. And also we looked into katakana words and non-word reading. Nevertheless, his actually performance is actually ceiling. He's absolutely very good. No impairment at all. So result of 2 studies on AS showed that AS, age 16, was a superior reader in Japanese, even when compared to Japanese university student. AS was clearly and typically a phonological dyslexic in English, and his performance on reading and phonological awareness test was significantly poorer than that of not only the English controls, but also the Japanese control. So, okay, so phonological processing phoneme awareness skills are essential in learning to read successfully in alphabetic languages, especially in English. So we are trying to ascertain why in AS is so poor at reading English, but not in Japanese. Phonological awareness and literacy are closely related. So if you are good at phonological awareness, if you have good phonological awareness skills, that leads to good reading and writing skills. And if you become reading and writing skills, better reading writing skills, then goes back to better phonological awareness skills. So they are kind of very closely related. The phonological processing phoneme awareness skills are not the most important metalinguistic awareness skills that we learned in Japanese and watching Chinese. phonological awareness skills become important for the older children in Japanese and Chinese. So therefore, AS's phonological deficit did not affect reading in Japanese, but did massively in English. So as I said, we are confirming that phonological dyslexia would be rare in two conditions, and we've already explained that. And AS's behavioral dissociation can be explained by this hypothesic granularity and transparency, because English is here and Japanese Kana and Kanji is here under the gray shade. So they don't produce phonological dyslexia, okay, while English does. So AS and then and now, during senior high school, AS was a vice president of the student union, and AS was an avid reader in Japanese. He wrote book reviews for the school library, and he used to carry Japanese paperbacks in his school uniform pocket all the time, and whenever he has time, he reads. AS was good at all subjects except for English, and was an able pupil, and hence his self-esteem was quite high. And in those days, Japanese English teacher at his high school didn't know anything about dyslexia. So he assumed that AS been very lazy because he is English native, he can speak English perfectly. So he doesn't practice English at all in reading and writing. That's why his English essay writing and so forth are poorer than his counterpart in his class. So he was absolutely, utterly wrong, but that was the situation then. So during university, AS went to an English-speaking university outside of Japan, as both his parents are native English speakers. Prior to entering university, he has extensive lessons for a year, and it took longer than other students. AS was awarded a BSc honors in computer science, and he received the dyslexia support all through the study at university. AS now is a very successful IT manager working at an international company. So, importance of self-esteem. AS would say in this radio interview that dyslexia is just a problem, not the problem. So dyslexia, although he was severely dyslexic in English, but that didn't affect his self-esteem at all. He knows that he is an able student, at least particularly in Japanese. So I'm going to move on to developmental dyslexia in different orthographies. Recently published books with my colleagues. First one is Dyslexia Comprehensive and International Approach with Professor Liori Farm-Pollack, my PhD student, postdoc, and now he's associate professor at IOE UCL. This was first published in 2012, but apparently it's so popular that they decided to reprint with a different cover in 2018. So I'm very pleased about that. And then second one is a book called Developmental Dyslexia Across Languages and Writing Systems. Editors are Professor Van Hoven, Perfetti, and also Pugh. And this book was based on a presentation at the following EU-funded workshop. We were all invited at Netherlands Institute of Advanced Studies, and end product was this book published by the Cambridge University Press. And I have one chapter on Japanese as well. And cultural diversity in the neuroscience of reading across different orthographies. Now I'm moving on to neuroscience of reading and English, Italian, and Finnish first. So Forrest et al., as I said before, they conducted behavioral study as well as neuroimaging studies. This is a PET studies with 36 English students, 36 Italian students. And the neuroimaging tasks were explicit reading experiment with the same stimuli from the behavioral task, and the implicit experiment, feature detection task, detecting the presence or absence of ascenders. Okay, and the baseline was just resting state. So this is the result. The first picture shown that English and Italian participant, the common reading areas for English and Italian, reading minus baseline for the implicit explicit reading experiments. So you can see the frontal lobe area, the temporal lobe area, and also temporal and occipital junction area. These all three areas are activated when both English and Italian student read these. The same was in the behavioral experiment. So this is in English minus Italian. So those regions of great activation in English during especially non-word reading is the left inferior posterior temporal area and anterior portion of inferior frontal gyrus. So these two areas seems to be more specific to English participants. And the Italian left planium temporale and superior temporal region was more active in Italian, regardless of word type. And then so we used this DRC, well, Puresi used DRC model to interpret the data, and Italian readers' strong activation to the on the left temporal parietal area is linked to phonological processing. And for Italian, the optimal reading strategy is sublexical phonological reading. So actually, we can actually interpret the PET data or neuroimaging data using the DRC model. Now, another consistent, I don't know what to do. Okay, another consistent writing systems, Finnish, we used, and we conducted the lexicality and letter length effect experiment using MEG data. And this was with all my female scientists from Helsinki University of Technology. Now it's called Aalto University. And this is essentially really the girls' power. I'm very proud of. Okay, so Finnish is a very interesting writing system. Finnish is consistent shallow language represented by 21 phonemes, as opposed to 44 phonemes in English. And the phoneme to grapheme correspondence is 1-to-1, just like Italian. The mapping from grapheme to phoneme are unequivocal, 1-to-1. And one particular interesting feature of Finnish writing system is Finnish is also an agglutinating language with many different forms and cases. So for example, talo, house, is one word. Talossa, in the house, is one word. Taloissa, in the houses, is also one word. So you can actually make infinitely long words, one word in Finnish. So optimal reading strategy is sublexical GPC. However, as with Italian, this does not preclude whole word lexical contribution during reading in Finnish. Okay, so this is actually MEG scanner, and this is the magnetic sensors covers 306 magnetic sensors covers all your head, and you put your head under this huge scanner. So MEG is a non-invasive method, which is based on measuring the weak magnetic field generated by synchronous activation of thousands of neurons. And MEG has excellent temporal and good spatial resolutions. So its temporal resolution is similar to EEG, but spatial resolution is much better than EEG. Okay, so experiment. We used the implicit reading experiment with 400 letter strings in total. So short word, short non-word, 100 each. Long word, long non-word, 100 each. Okay. So this is just an example of how data would come out. This is from one patient, sorry, one participant showing long non-word activations. And this is the dipole we actually identified from this particular area, left superior temporal regions, superior temporal region. And so then once we identify the dipole, we then actually using their own MRI model, MRI image, to superimpose this particular area so that we are sure where is the actual activation taking place. Okay, and then this is the result. A is showing the occipital lobe activation, 0 millisecond to 200 millisecond. So here you can only see the length effect, no lexicality effect. So short word and short non-word is the same, and the long word, long non-word is the same. So occipital cortex, they are not at all interested in lexicality, but the actual length effect. And then B is showing left superior temporal lobe, 200 millisecond to 600 millisecond. You can actually see length by lexicality interaction here. The shortest duration is long, short words, and then next long words, and the long words and short long words, not much difference at all. The longest duration is shown by the long non-words. So here you can actually see the length by lexicality interaction. So where is actually the area in the cortex? So left superior temporal lobes showing length and lexicality interaction. It's just actually here. And then the duration of cortical activation, this is the actual long non-words. Okay. And long, so we measured this sort of duration. So half the length of the things of this, and here and here. So as you can see that the current MEG data support further lends support to Poresetta's PET study, as well as the conjecture that optimal reading strategy in Finnish is sub-lexical GPC. So we actually compared Italian PET studies and Finnish MEG studies. Very similar areas are activated by neurotypical individuals. Okay. So now looking at biological unity in dyslexia across different orthographies. Now first one is English, Italian, and French. So Forest et al. Conducted another study including 24 each university students. Half of it is dyslexics and half of it normal controls. And of course, in Italian, they asked them to bring their documented history of reading and of spelling difficulties. But of course, Italian, such diagnosis is rare. So instead, they conducted a screening test. And out of 120, they chose bottom 10% of reading and writing speed latencies. Okay, and thus they are 24 university students. Each country represents half controls and half dyslexic individuals. And then this is the data. Reading minus baseline, all the normal readers data. Again, very similar to Italian and English participants data. Very similar areas are activated. Now, reading minus baseline, all the dyslexic individual data, you can see here, some things missing here. So dyslexic PET study showing that same reduced activation in the left middle inferior and superior temporal cortex and in the middle occipital gyrus among English and French and Italian dyslexics. Hence, here showing biological unity. And then brain region, which was significantly more activated in all normal controls for all dyslexic readers. This is actually showing B. And then bar graphs D illustrates the profile of regional cerebral blood flow, how strong this activation is, increases for reading in control and dyslexic group from these 3 countries. So these are the primary data. So Forest's behavioral study showed that English, French, and Italian dyslexics were equally impaired relative to their controls on reading and phonological tasks. Similarly, the neuroimaging data during explicit implicit reading showed the same reduced activation in the left middle inferior and superior temporal cortex and in the middle occipital group among English, French, and Italian dyslexics, hence showing clear biological unity. So this is neuroimaging actual research showing in alphabetic languages. Left hemisphere reading related sites are usually under activation or hypoactivation. Those areas are left temporal parietal and the left occipital regions. And these under activation or hypoactivation is particularly pronounced during printed word processing or phonological processing. Now, neuroscience of reading in different orthographies, biological unity. Now I'm talking about English and Japanese Kana. So this is with my colleagues, with Professor Kondo, published in 2015. And remember, AS was behavioral studies showed that he was superior reader, but he was so impaired. He was typical phonological dyslexic in English. So we gave AS two tasks, phonological description in English and also Japanese katakana. So AS and English control participants were asked to respond yes to pseudo-homophones such as brain, B-R-A-M-E, sounds like a real word, you have to say yes in English. And AS and 6 Japanese control participants were asked to respond yes to pseudo-homophones such as gakusei, meaning student, normally written in kanji characters, but here we transcribed into katakana. So they have to say, when you read it, gakusei, does it sound like a real word? You have to say yes. So the stimulus word, non-words were presented at 0 millisecond, and we measured minus 200 millisecond to 800 millisecond during each swipe or each task. So AS showed reduced activation, low amplitude at 204 milliseconds in left superior temporal gyrus in both English and Japanese, and the left STG is linked to phonological processing. So this is the actual result. Reduced activation, so low amplitude at 200 and 400 milliseconds. You can actually see AS in Kana and AS in English. They're very similarly activated, but amplitude are much lower than English controls and also Japanese controls. The area of activation is actually superior temporal gyrus, English clusters here, and Japanese clusters here, something very similar. And AS also has superior temporal gyrus activations for both English and Japanese. But as you can see, the activation level is much, much lower. So now we brought in MEG Finnish data. And as you can see, something very similar to English and also Japanese neurotypical individuals, okay? So AS also has similar activation here in the superior temporal gyrus, but amplitude is very low. The activation is very low. Okay? So here also we are showing biological unity in Japanese Kana and also English, as well as I guess Finnish too. So neuroscience reading in Chinese, this is the last slide. In Chinese, no biological unity. Is this an anomaly? Okay, so stories so far. Cultural language diversity is English, French, and Italian, both in the behavioral and neuroimaging data. Dyslexia in these languages has a universal biological origin. But Taeko et al. Challenged this view with fMRI study employing Chinese neurotypical and dyslexic readers as participants. So Taeko et al.'s assertion is this. In Chinese, graphic forms, characters map onto morphemes, meanings. The phonology of written Chinese is defined at the monosyllabic level and with no parts of a character corresponding to phonemes. So Chinese, as I've been saying, that is a syllabic language, not phoneme-based language. So reading difficulty in Chinese evolved not only from the poor quality mapping of orthography to phonology, but also from an impaired connection between orthography and semantics. Therefore, according to Seok et al., brain activation abnormalities associated with impaired Chinese reading might differ from that associated with impaired English reading. So they use the behavioral data, RTs and accuracy. RTs of neurotypical readers for homophone judgments were significantly shorter and fewer errors than those of dyslexics. You can actually see this is RT, this is accuracy. You can actually see effect size is bigger in reaction time than accuracy. Okay, so this is a neuroimaging fMRI data. So this figure shows the cortical activation associated with homophone judgment, contrasted with font size decision in Chinese neurotypical and dyslexic individuals. And direct comparison of both oxygen level dependent show that strong activation was found in left middle frontal gyrus. Here, the by neurotypical readers. So this is the this N is a neurotypical, and I is the red one is impaired readers. Okay, so you can actually see BA9 much strong activation by neurotypical individuals than dyslexic individuals, but this conversely, dyslexic readers have a stronger brain activation in left inferior prefrontal gyrus. Have a look at this, quite strong activations in BA45 than the normal readers. So the Seok et al. Say that probably this can be considered as compensatory mechanism, that because they can't use BA9 efficiently, they have to use BA45, different sort of part of cortex. That's their interpretation. So Seok summarizes the fMRI study. Previous research in English found reduced activation in the left temporal parietal region as a biological signature of reading disability. But Seok studies show that reduced activation of left middle frontal gyrus as a neuroanatomical marker of Chinese dyslexia. Therefore, left middle frontal gyrus is a crucial brain area responsible for skilled Chinese reading. The study also showed, as I said before, hyperactivation of the anterior portion of the left inferior prefrontal cortex, BA45, in Chinese dyslexics. And they actually think that this could well be a compensatory activation. So in summary, different cognitive processes are involved in reading in different orthographies, which are primarily due to different characteristics inherent within a given orthography. These differences give rise to different prevalence rates of developmental dyslexia. Yet, impaired brain activation patterns were similar, at least within the development, within the different languages where a phonological deficit was major cause of developmental dyslexia. That is English, Italian, French, and Japanese Kana. So implications are, when developing intervention programs for developmental dyslexia, these differences should be taken into consideration. And what's happening in Japan is because Japanese researchers and educationists knew that the research in developmental dyslexia is behind compared to, say, English and Europe or other countries. So they tend to borrow whatever the intervention programs that, say, English researchers have developed. We borrow them, we try to use them in a Japanese language context. But of course, it doesn't work very well. So this is essentially when developing intervention programs for developing developmental dyslexia, and actually addressing this to non-English countries, I suppose. This difference should be taken into consideration. And thank you very much for listening. And any questions? I know I'm a bit over time, sorry.
Thank you so much, Taeko, for this fascinating talk. There is one question in the chat. I don't know if anybody has any questions that they want to ask. right now. Maybe we have 5 minutes. Brian? You're on mute, Brian.
Thank you very much, Taeko. That was fascinating. I'm very glad to see that AS has turned out all right.
Yes,
and that you followed up his condition and other relevant conditions in such an interesting and systematic way. Can I just make a comment about not your work, but about work you cited by Seok and Lehigh Tan and others? I just find that their results completely incredible, frankly. And the reason I find it incredible is because if they are right, then the key areas for Chinese reading are in the frontal lobe. And we know from studies of acquired dyslexia, the work that we did a long time ago, that if you damage the same areas in Chinese brains as you damage in English or Italian brains, you get acquired dyslexia. So you don't get acquired dyslexia if you damage these frontal areas that Seok identified. So I think that there's something very, let's say, fishy about her results. And one thing that you actually, it occurred to me that you might have comment on here. You mentioned compensatory, but when you're learning Chinese or Japanese, as you mentioned, you do lots of writing practice.
Yeah,
a lot of motor,
yeah.
a lot of motor work,
yeah.
and no doubt motor work will perhaps be a bit more frontal, though I expected something in motor area as well, which I don't think Seok found. So, I mean, there might be something going on there, but frankly, I just don't really believe that Seok's work really identifies reading areas in frontal areas of the brain.
Yeah. I think, Brian, you've got a valid point. I mean, these neuroimaging data are always dependent on the task and what sort of a task they've actually conducted. And also, although they say the homophone judgment and so forth, homophone judgment in Chinese characters are very different from homophone judgment in English, for example. So you cannot just actually equate these two very different sort of orthographies. That may be one of the reasons, but I'm not too sure whether kind of these developmental sort of dyslexics versus the acquired dyslexics, whether there might be kind of some sort of fundamental differences there or not.
Yeah.
And also their definition of developmental dyslexia probably is quite different from the definition of English developmental dyslexia.
Right, that's a good point. I long time since I read that paper or talked to Lehigh Tan.
But I was writing this, and I remember, Brian, we worked so hard for our very first paper in cognition, haven't we?
Yeah, yes, we did. And
yes.
I remember we went to AS's school.
Yeah.
And we tested all those kids whose spoken English was not great. It's like A-level students learning a foreign language here, whereas AS, of course, is completely fluent in English. But they were all better on the phonological tasks, as you point out, than AS was. Yeah.
Quite. It was really interesting, and I really enjoyed working with Brian.
Yeah.
That's a brilliant time. Yeah.
Thank you. We have time for one more question. Tali?
Thank you. Thank you very much. It was really interesting.
Thank you.
Especially I like the MEG work that you mentioned. And I really agree with all your conclusions.
Oh, thank you.
I did want to mention that we have support for your conclusions from Hebrew.
Oh, right. Thank you. Really.
As you mentioned that there are two versions of script with transparent and non-transparent. And we do see within subject differences in dyslexic between, you know, what is impaired in the brain when they are reading the transparent script and the non-transparent script, and this is within subject. So I think it is really great. I totally like your conclusions.
Thank you so much.
Thank you very much. I wish we could take more questions, but we have run out of time severely. The recording of the seminar will be available on our YouTube channel, so please tune in if you want to see it again. I know I will. Taeko, thank you so much for your time
Pleasure.
today, and thank you everyone who was able to come and stay for the rest of the talk.
Yeah, thank you very much, everybody. And I'm sorry I overrun. I knew I would because I had so many slides.
There's so much to say. There's such an amazing story.
Thank you very much, everybody.
Thank you, everyone.
A nice evening.
Bye.
Bye.
That's it. If ops.x